Hello everyone, my name is Hunter and I'm going to walk you through my operating system. So to start, it has a basic implementation of all the problem set requirements with some minor additional features including command line utilities such as cat, ls, and ps, as well as the ability to set the system date with a text format as opposed to using a number. And then for the final project, I did two unrelated things. The first was some command line parsing enhancements, which allow you to navigate the current line using a cursor and access previous lines. And finally, there's a basic priority scheduling algorithm with a nice command to allow you to set the priority of a target process. In terms of memory allocation, the operating system uses a first fit algorithm, and the managed memory starts after a region reserved for the LCD screen. Some memory identified by PID-1 is held indefinitely by code that performs various initialization functions and spawns the shell, because that's how I chose to implement multi-programming. So if we demonstrate that by running memory map, we can see that the regions associated with PID-1 include structs allocated for various static I/O data such as devices and files. That's what these regions of 24 and 16 bytes are. And that means that the shell process has PID0 and any further mallocs required by the shell are associated with PID0. In terms of device-independent I/O, the suggested abstraction pattern of devices, files, and streams are all implemented. There's a ls command which displays all the files in the operating system in a single top-level directory. And then finally, in terms of accessing the same file through multiple streams, only one stream can be open to a file if that stream is in write mode. So we can run ls to see our files, we can open one, say the LCD, in write mode. Then if we try to open another stream, even in read mode, that's going to be a problem. The implementation of multi-programming, the shell is spawned as the first process, and then the initialization code busy waits until a sysdig timer interrupt occurs and the shell starts for real. The shell is guaranteed to not be killed, so there's always one process, and the SVC spawn call is done with a pointer to struct to allow for more than 4 arguments into an SVC call. Interrupt priority levels are set as was suggested by one of the application notes, with the supervisor calls having the highest or least important priority and the hardware interrupts having the lowest or most significant priority. The flex timer maintains a system date time as required by problem set 5, and that date is printed with separate values for the high and low bits, like this, to handle the 64-bit size. Additionally, I added the feature to allow formatting in a text format as opposed to a number of seconds. So you can set the date like this and then display it again, obviously. There's also some specific errors for invalid formatting, so if you try to send it a string that's too long, that's recognized with a specific error message, or if you try to send it, say, an unreasonable number of seconds, that's recognized with a specific error message. So the first thing I did was add some command line interface enhancements. So basically I wanted to mimic the use of arrow keys in the shell on various other operating systems. So that includes cursor movement along the current line. So if I type echo hello world, let's say I make a mistake, I can move the cursor along the line and use the backspace button to fix it. Then the second feature is the ability to access previously executed lines. So if I type another one, just for demonstration, pressing the up arrow allows you to access the previous lines, and you can edit them in place and run them again. In terms of how these command line enhancements were implemented, the first step was to abstract the concept of a line in the terminal. So that's what we see on the right with this struct, and the key attributes here are the length of the line, the cursor position in the line, and a char star for the string data itself. And then these line structures are stored in a doubly linked list, which facilitates accessing them in a specific order and in both directions. So anytime a new command is input, it enters the head of the doubly linked list, and the global variable is maintained for that. Finally, there's a bunch of additional logic for managing this data structure, as well as output to the terminal based on what type of character was input. So it could be regular character, a backspace, an up or down indicator, and just a lot of additional if statements to that effect. The second thing I implemented for the final project is the concept of priority scheduling. So each process has a priority value that determines how often it is scheduled, at least relative to other processes. And this priority value defaults to 0, which is scheduled most often when a process is first created, but then it can be set by a new supervisor call called nice, and it's set within the range of 0 to 10. So I'll talk a little bit more about that implementation in a second, but first a little demonstration. So when the operating system first starts up, we can run this ps command to show that there's just one running process, which is the shell. Then I've added a flash LEDs program, which spawns separate processes to flash different LEDs. So if we run that, we can see that the orange and blue LEDs have started flashing, and we can see that there's a process for each of those LEDs. And we can see the priority for all three of the processes is 0, which is scheduled most often. But then if we up the priority number for, say, one of the processes, we can see that the orange LED has now started flashing less often, and that's reflected in the output from the ps command as well in the priority level. And if we set it back to the priority of 0, it'll start flashing just as frequently as the blue LED again, and that's reflected in the output from ps as well. We'll talk more about this virtual priority column in the future. The implementation of priority scheduling included adding several new fields to the PCB and an update to the algorithm in the scheduler so that it counts up to the priority level of a process before actually running it. So each PCB has a priority value as well as a count, which I called skipped count, of the number of times the scheduler has considered the process but skipped it instead of scheduling it. So on the scheduler side, the algorithm checks if the skipped count is less than the priority, and if so, just implements that skipped count. Otherwise, the process is actually scheduled and the skipped count is reset. So a pretty straightforward implementation, at least to start. The basic implementation of priority scheduling that's been laid out so far has a drawback, and that's that if every process is set to a high priority number, the scheduler will spend time unnecessarily looping through the PCB list, skipping all the processes. So if we run our flash LEDs program, and we set the priority of all the processes to be the highest value possible, we can see that each process is going to be skipped 10 times before being run. So the solution for that is to manage another priority value, which I called virtual priority, that is the original priority value minus the smallest priority among all processes. So in this example, despite all these processes having a priority value of 10, the virtual priority is 0, meaning that the scheduler will actually run them the first time they are encountered. And for further demonstration, if we set the priority of one of these processes to be a lower value, so scheduled more often, we can see that the virtual priority values have adjusted. So now process 2 and process 0 are being skipped 5 times before being run, but that is the desired behavior as it allows process 1 to run more often as requested by the user. And everything is not skipped 10 times and 5 times. Process 1 is run the first time it's encountered because of that adjustment we made with the virtual priority. Adding the concept of virtual priority involves several different steps. There's a global variable maintained for the priority offset, which is the lowest value among all the process's priorities. This global priority offset needs to be updated when executing nice to change the priority of a process, or when a process goes away, that is, when it is leaped. Finally, the virtual priority value needs to be kept up to date for each process, and that's handled by the scheduler every time it inspects a process to determine if it should run. So in summary, my operating system probably looks a lot like other operating systems in terms of implementing the problem set requirements. For the final project, I added some command line interface enhancements, the ability to move a cursor around and access previous lines, and then priority scheduling. In terms of future work, I think it would be nice to have some user-based protection for the nice command, since it's a little scary that anyone can go change the priority of any other process. But that's all I got, and thanks for watching.